So let's look at the question together. The question says we should investigate for which values of R is the sequence R raised to power n over n factorial convergent. So the solution, we let an equals R raised to power n over n factorial. Then we'll now consider the scenarios with R equals 0. So if R is 0, an will be 0. That is substituting 0 for R in an. So that will be 0 raised to power n, which is 0. And 0 factorial is 1. Or whatever you are dividing 0 with is 0. So an is 0. Thus, an is convergent when R is 0. Now, consider when R is positive. That's the meaning of greater than 0. So that we can find an plus 1. So an plus 1 will now be R raised to power n plus 1 over n plus 1 factorial. How do we achieve that? We substitute n plus 1 for n in an. And that equals R raised to power n times R over n factorial times n plus 1. Now we have used the definition of n factorial, which means n plus 1, n into n minus 1, n minus 2, and so on. So n plus 1 factorial will now be n plus 1 times n plus 1 minus 1 factorial, and that will give us n factorial. So if you rearrange it, R raised to power n over n factorial times R over n plus 1 will give us this term. This is R raised to power n over n factorial. That's our an. That's our an. So an plus 1 will now be equal to R over n plus 1 times an. And I can rearrange it by saying an plus 1 over an equals that. Now, R over n plus 1 will be less than 1 if n is greater than R. For instance, if R is 1 and n is 2. So 1 over 2 plus 1 will give you 1 over 3. And of course, 1 over 3 is less than 1. So if you take another value such a way that n is greater than the value of R, it will always be less than 1 when R is less than n, or n is greater than 1. So take limit of that. To take limit, you have 0. So an is also convergent when R is positive. That's the meaning of R greater than 0. Let's now consider when R is less than 0, that is negative. So we take absolute value of an, meaning we are taking absolute value of R raised to power n over n factorial. So separating the absolute value using one of the rules of absolute value function. So we can say that is absolute value of R raised to power n over absolute value of n factorial. Now take note that limit of absolute value as n tends to infinity is going to be 0. Then the limit of an itself as n tends to infinity will also be 0. So taking limit of absolute value of an is same thing as saying taking limit of R raised to power n over n factorial, and that will be 0 as n tends to infinity. As n tends to infinity, not 0. As n tends to infinity. So that will be 0. Thus, we can also say that an converges when R is negative. Now, we have considered 3 situations or 3 scenarios when R is 0, when it is greater than 0, and when it is less than 0. So you can see that in the three cases, the sequence tends to 0 when n tends to infinity. So in each case, it converges. So we can now conclude that the sequence r raised to power n over n factorial is convergent for any r. It's convergent for any r. So let's take this. For any real number a, we are asked to show that the limit of 1 plus a over n, everything raised to the power of n, is e raised to power a. We are asked to show that that limit equals that. So solution, I will change the function to x. So let f of x equals 1 plus a over x, everything raised to power x. Or you want to say y equals to that. Now, I will take ln on both sides. That's ln y equals ln 1 plus a over x raised to power x, which is the same thing as saying ln y equals x ln 1 plus a over x, using one of the laws of logarithm. I can take LCM of the term in bracket, so that will give me ln x plus a over x. That's taking LCM of the term in bracket. So ln y equals x. I will now apply another law of logarithm. So that will be ln x plus a minus ln x. Now, the right-hand side can be written as this x. I can write it as 1 over x. 1 over x. If you take reciprocal of 1 over x, it gives you x. So you come back to this. Now, the essence of doing that is to be able to apply what we call L'Hopital's rule for limit. So this will now be ln x plus a minus ln x divided by 1 over x. So I can take limit of both sides as x tends to infinity. So if you take limit of both sides, you have limit of ln y as s tends to infinity equals limit as s tends to infinity of ln x plus a minus ln x divided by 1 over x. And this will be if you substitute the limit, the limiting value, which is infinity, that will give us 0 over 0. And this is indeterminate. And indeterminate is not an accepted answer. So we have to do it for that. Now, using L'Hopital's rule, and what does L'Hopital's rule says? L'Hopital's rule says if you have the limit of rational function of this type, you differentiate both numerator and denominator separately. So by L'Hopital's rule, limit of lim y as s tends to infinity equals limit as s tends to infinity of, so I will now differentiate the numerator. Differential of ln x is 1 over s. So differential of ln s plus a will be 1 over x plus a minus 1 over s. I have differentiated the numerator. Differentiate the denominator, that will give me minus 1 over s squared. That's the differential of the denominator. So I can take the LCM of the numerator on the right-hand side. So limit as s tends to infinity of, I'm taking LCM of that. So that will be s into s plus a. And that will be s plus a goes in s plus a, you have s left. So you have x minus, s goes in x and you have s plus a. So this minus will affect both to be minus x minus a over minus 1 over s squared. And of course, this will be limit as s tends to infinity. This minus will take care of this, this s will take care of this s. We have minus a over, let me write it in the next line. So this will be limit as s tends to infinity. You have minus a over x into x plus a times minus x squared over 1. So ln y will now be equal to limit as s tends to infinity of course, this s will take care of one of these. Negative times negative will give us positive. So you have xa over x plus a. Now, because the limit is approaching infinity, we have a rule that says you divide both numerator and denominator by the highest power of the denominator. So the highest power of the denominator in this case is x raised to power 1. So I will divide both numerator and denominator by x. And that will give me a over 1 plus a over x. So I will now substitute infinity for x. So this will give a over 1 plus a over infinity. And of course, any number divided by infinity is 0. So this will be 1 plus 0. which is 1. You have A. So that implies that lane Y equals A. And the base of A, the base of lane Y is E. That's lane Y means log to base E. So Y equals E raised to power A. That is, don't forget, Y is our f of s, which is 1 plus A over X raised to power X equals to A. Hence, limit as n tends to infinity of 1 plus A over n raised to power n equals E raised to power A. End of proof. Thank you.